don't even say.
I thought it was right.
No.
They're wrong. So no, like not really. I mean, if he's around, I was gonna just like, we're gonna give him the reach around this back to class. And he's gonna go to the so I probably would have started there. The last part of that is all the work, and like this is all the stuff that other parts of the setup to the work, and it's just way too much. Get to. I'm good. I was just gonna go over the other two. Was that your end stuff?
Yeah. And also 3:30.
Thank you. Did you get this done? No.
Did anybody get it done?
Wait, do you need
What, the
to say
3:31?
Yeah. I've got 2.5 hours after this class before it's due.
Exactly.
I actually don't know.
Like you do, but
We don't need to get 100%.
I do not.
Like, I might just like do what I can with the L on it. Like,
I started, I haven't finished.
I have no clue what I'm doing on that stuff.
Jackson, I would say the post-ball man.
I do
It's gonna be
Post-ball man.
I'm way more excited for that than the actual ball.
Oh, yeah.
Yes. Okay, we've beat the ball for a long time.
What?
We've beat the ball for a long time.
no, that's what we're talking about.
No.
That's so late.
It's like after winter, so it's
Let's
go. Let's go.
Or like, you know, whatever, my money's
I think
I've been there for 5 hours. No, you have no idea. I've been there 3:30. Yes.
Wait, what are you, Jackson, are you just helping us out? Or, I mean, are you helping us out?
Do you want me to go some details?
What, I know your shots are good, right?
Football on Monday?
Yeah, I actually go to my
Yeah, he's not right, but like,
He's like supervising the football staff.
we had like taste test, you know,
Oh, yeah.
a little bit of salt.
Okay, cool.
We have to take a quiz on what the rules
Just
were.
go ahead and spit.
Yeah, but I didn't actually like.
No, the rules that they ask you in the quiz is like, how many girls do you need on the field to play a game?
Yeah, it's like,
Like, and like,
What
can you drink
color-
alcohol before a
yeah,
game?
or like,
I feel like it'd be more fun if you were drunk.
Where that's the best.
I mean, yes, it would be way more fun, but like, then
Wait, is that a requirement for IF?
We should wear it on the outside.
I mean, I never knew anyone.
Flood it up, please.
Except if it's right after this class. It's also just trying to change junior hours.
Alrighty, before we get started, quick announcement on the exam that's is scheduled for a week and a half from now. I have made an executive decision to push the exam back by 1 week. I've got a lot on my plate right now personally, so I can't guarantee I'm going to get homeworks back like a super snappy rate. So to make sure you guys have time to wrap up the Chapter 6 material, get homeworks back and review them, and that I'll be available to help you guys review for the test. I think it's better if we push it back to November 16th. Any objections to... That's a Wednesday.
Do you know if that's gonna be in class?
So my plan is to, I'm gonna hand it out in class, you're gonna have the hour and a half in class, and you'll have the option of taking it home that evening and turning it on Friday. So think of it like an in-class exam, but without the constraint of having to finish it in a strict hour and a half. Alright? Cool. So on Wednesday, we wrapped up with the idea of the stream function. Remember, so the stream function comes from the fact that we said for incompressible fluids, we have the continuity equation written like this. And so we defined a function that we called psi, and we defined this for steady two-dimensional plane flow such that u is equal to d psi dy and v is equal to negative d psi dx. And remember what was special about this, choosing a function from which we get both velocities is that if we plug u and v in and as for our velocity field and we take the divergence of this velocity field, we always get 0 because it ends up being partial psi, this ends up being partial squared x partial y psi minus partial squared x y psi, identically 0. So if we define our velocity field in this special way, such that we have one function that constrains the entire thing, then we're guaranteed to satisfy incompressibility. So we got to this definition, and additionally, let's see, what are the, my eraser. So there's this fact about psi, it always satisfies incompressibility. And additionally, I'm just going to list some of the properties of the stream function. So for the stream function psi, satisfies incompressible continuity equation. Psi is constant along a streamline. And then, partly as a consequence of this fact, remember that if we're interested in figuring out the flow rate, the volumetric flow rate of a fluid between two streamlines, then what we got was Q is simply equal to, say, the difference between streamlines. Let me. If you take the stream function, which is constant along two streamline, or along a given streamline, and you take the difference between the stream functions on the streamlines, what you get is the flow rate between them. So where we left off was I was about to throw an example up that lets us put some of these concepts into practice. So suppose we have the velocity field shown here. This is a two-dimensional incompressible flow by assumption with velocity components given here, u, v, and w equals 0 as a consequence of the two-dimensionality of the flow. So 3 questions to answer. 1, does this flow satisfy continuity? We've given velocity components, but we haven't yet actually said whether or not they come from a stream function. Does a stream function exist? If so, find it and then plot the velocity field. So, go ahead and write this up. U equal a x squared minus y squared. V equals -2 ax y. All right, so question 1. Satisfy continuity. We've said that it's an incompressible flow, right? So that means that the form of the continuity equation we use is simply that the divergence is equal to 0. This is the continuity equation for incompressible flow. So what we need to do is say du dx plus dv dy is equal to what? So let's go ahead and have Joey, if you want to give me du dx and Andrew, if you want to give me dv dy.
3x, which is 2x.
Well,
Alright.
2ax, right? 2ax. A is a constant. I forgot to write that up here. An unknown constant. All right.
dv dy is negative 2as.
So we get 0. Which tells us that yes, this two-dimensional flow satisfies the continuity equation. Simple as that. All right, so two. Is there a stream function? And if so, find it. So what do we have to start with here? We have only the relationship between the stream function and the velocity components. Psi dy is equal to u. So we have these two relationships between psi, mu, and v. So, considering we have derivatives, we have known expressions, what would be the logical next step? Integrate, right? So let's go ahead and we'll start with v, actually. This is so we have here that we say v, which is negative 2axy, is equal to negative d psi dx. First thing, we get rid of its negative sign, both sides, and we integrate both sides with respect to dx. Which gives us psi is equal to ax squared y plus, and this is the important thing when you're coming up with stream functions, an unknown function, we'll call it f1 of x. Oh, sorry, of y. My bad. Now, we had a similar thing come up in class on Wednesday where integrating, we had left over this unknown function of the variable that we were not integrating with respect to. And just, just see the logic here that if we're taking the derivative of this with respect to x, this disappears entirely, so it won't show up in v. So the way we determine what this unknown function of y might be is now we come up, we bring this expression in and integrate it and compare the two results for psi and match up functions. So for u, we have a x squared minus y squared is equal to partial psi, partial x, or sorry, partial psi, partial y. Integrating with respect to y now. We get psi is equal to ax squared y minus ay cubed over 3 plus f2 x. All right. So there's not really a real systematic way of doing this. Well, other than you come up with your two separate estimates of what psi is, and then you just compare. You say, all right, you got your x squared y. We're looking for a function of y. That's satisfied by this right here. And then we're looking over here for a function of x, which we don't, it doesn't show up in this expression. And so the only thing that f2 of x could be is a constant. Which means that these two separate solutions for, say these two separate solutions for psi give us psi equal to ax squared y minus ay cubed over 3 plus a constant.
How did you determine that F2 is actually constant?
Because this is the same expression, right? We have just, but we're just missing different pieces.
Sure.
So if there were a function of x, it's not over here, it would show up over here. And over here we're integrated with respect to x. And since there's nothing, you know, it doesn't show up here and it doesn't show up there, all it can be is a constant, something that disappears with respect to both x and y.
And then you just know F1 of Y disappears.
I know f1 of y,
Oh, so
it shows up right here. There's a function of y alone right here. So.
Why did you do d psi dx times dx? Is that just the same multiplying dx to either side?
Over here? Yeah, it really is. Yeah, it's just kind of semantics. People who are really picky about their calculus would get grumpy with you multiplying over a partial x to one side because it's a partial derivative. But it's never caused me problems. So yeah, you could just multiply this over and then integrate with respect to over here, or you could say these basically cancel each other out. We end up with this side. Yes, good eye there. All right, any other questions about this process? The idea is you really only have, you have u and v, you have two unknown variables, or you have two known variables, you integrate them with respect to x and to y, and you just compare the answers, and sort of by looking at them together, you come up with a cumulative expression for psi. All right. 2, we have then psi is equal to ax squared y minus cubed over 3 plus constant. Let me. All right, and the last task is to draw the velocity field. And the easiest way to do this is actually to start by drawing streamlines. Remember, we're going to take advantage of this identity of the stream function right here. So let's go ahead and say, let's take this expression, let's set it equal to a constant, right? That means if we say that c is equal to ax squared y minus ay cubed over 3. We can go ahead and move this over here and come up with, well, I guess first, let's go ahead and first say, let's assume that this constant is 0, right? Remember I said that it's constant along streamlines, and to plot a different streamline, you just change the constant that psi is equal to. So if we just arbitrarily, we could choose anything, we could choose 3, 4, 5, doesn't matter. Let's go ahead and assume first that c equals 0. So we get ax squared y is equal to ay cubed over 3. Now, the first thing we can do is put my eraser down over here. Let's cancel out these a's from both sides. And there are three possible solutions to this expression. One of them is, well, y could just be equal to 0, right? That's one solution here. We have y equal to 0. Or if we divide through by y, get rid of that, this turns into a squared. We end up with y equal to square root of 3 times x plus or minus. So y equals plus or minus square root of 3 x. So these are going to be these are going to describe three streamlines right off the bat in our velocity field. And there's a reason that we chose x. There's a reason that I chose c equals 0 is I know it's going to do some cool stuff. So our first, let me change colors here. So y equals 0, this one's easy, it's just along the x-axis, right? So there's one streamline. Positive square root of 3x means it's just something greater than the slope of 1, so it's actually at a 60-degree angle from the horizontal. And then negative square root of 3x. All right, next question here is, we have our expressions for u and v. What would be our stagnation point? So one way of finding the stagnation point is actually to solve for a point where both of these are 0. The other one is to recognize, remember, streamlines, flow is always along streamlines, right? So the only way that streamlines can cross one another, like they do right here, is if the velocity is 0, right? The flow can't cross streamlines, therefore streamlines only cross one another if there is no flow. So that means that here's our stagnation point. And because flow can't cross streamlines, that means the remaining streamlines, I'm going to draw them in as a different color, have to run tangential to these. So that means this has to be a streamline, this has to be a streamline. These would all be streamlines. Does that sort of logical step make sense to everybody? All right, and then the last thing to do here is, well, we have some sort of notional streamlines drawn in here, is figure out what direction the flow is going in. Right. So let's go ahead and just pick a quadrant up here. Let's say with a positive x and a positive y. What is our velocity component? Positive or negative? It's going to be, if we just take any arbitrary x, any arbitrary y, and they're both greater than 0, we plug them in here, product of two positives is going to be a positive, so your velocity is going to be negative, right? Assuming A is positive. This all depends on the sign of A, of course. But in the case that A is positive, that means that anywhere up here in this quadrant, the velocity is headed downward. So it has to be traveling along this direction in these streamlines. And along this direction in these streamlines. Over here in the negative quadrant, positive value for y, negative value for x, we end up with a positive v. So just like we already drew in here, that implies that our flow is heading in this direction. And if we went ahead and did this for each quadrant, you know, we would see that the flow and there we have a sketch of streamlines and directions. And remember, we would be able to draw out each of these streamlines if we just picked different values of our constant to which we set our stream function equal. And to demo this for you, in case you don't really believe me, I wrote up this little MATLAB script that, alright. So, there we go. Alright, so you can see up here I wrote out the expression for psi that we had, right? Negative x squared y plus y cubed over 3. And so if I plot out different lines along which that expression is constant, what I get is, give us a moment, there we go. Same thing we just drew out on the board. These black thick lines are where it's equal to 0. These red lines are where it's greater than, it's a positive number, so it indicates one direction of flow, and the blue lines are where it's a negative number, indicating another direction of flow. And so if I, well, it's actually almost right at the top. That's a mess. But what's cool about this is, I want to duplicate this so I can. All right. So what I want to get across here is that the stream function is really powerful because it doesn't matter, you know, what the stream function is. You can pick any function, and if you take the derivative with respect to x and the negative derivative with respect to y, or vice versa, you will get velocity components that then satisfy continuity. So if we want to just make up a random function up here, we could say x times y squared plus pi, and let's make this y to the 5th power. We ran it and plotted out. We have a flow field with streamlines that satisfy continuity. So it's a really useful mapping tool because I want to point this out in particular. Just what we did on the last slide, for example, or on the up on the board here, where where the flow velocity was equal to 0, right? Those places where the flow didn't cross. Those are actually really useful tools for modeling, for example, walls in a flow. Remember, streamlines make really good analogs for frictionless walls because flow never crosses them. So if you're able to tell the streamlines where to be somehow, for example, if we just happen to have some geometry that had some crazy curvature going on, and we wanted to model the flow around this geometry, we could plug in this function, say, set the stream function equal to 0 to indicate the position of some body, and then we could plot the streamlines around that body. All right. Okay. So, like I mentioned, this example is a really good way of approximating what we call corner flow. For example, if we call these lines here sort of imaginary walls, what we get are the streamlines that occur for inviscid flow in an interior corner. So what we're going to try to get through for the rest of today is, how do we finish this up? We're going to be turning our sights back on conservation of linear momentum, but instead of dealing with it in a control volume sense, we're now going to be focusing on the tiny little differential fluid element, just like we did with conservation of mass earlier. So give me a moment to, well, anyway, but the goal of doing this is that whether we get to this by the end of today or not remains to be seen. But by the end of this lecture, or this material, you should have an idea of how we go from the F equals ma that we all know and love, that describes like rigid body dynamics, how we go from that applied to a solid to a point in space in a fluid field, and how that motivates the flow in a field. All right, like in particular, we're interested in what makes up the forces on this side, and how do we write the acceleration on the right-hand side. So this should be review at this point. Conservation of linear momentum. Remember, we say the force is equal to the Lagrangian rate of change of momentum, which we write as p, where p is, for example, equal to the integral over a system of its velocity times its elemental mass. So the way we usually write this, as I said, with solids is ma. And in chapter 5, we went over how to go from the system representation to a control volume representation, which is fixed in space. So what we're doing now is going from this control volume representation down to a single point in space. So we can get to the single point space by using either the system or the control volume representation. It tends to be pretty easy to do it using the system approach, because if we write out this expression up here, small force equal to the rate of change of a small amount of momentum, v delta m, we know that for a system, mass remains constant, right? Lagrangian rate of change of mass is equal to 0. That is conservation of mass. That's the continuity equation. That's what leads to all of what we've been doing. So if we're assuming that we take a tiny little system of particles and we apply a force to it and its momentum changes, we know that that change in momentum has to come not from a change in mass, but from a change in the velocity, which we write as acceleration. So this is all just a roundabout way of saying, yes, if we pick a really tiny little packet of fluid particles, then the sum of the force is equal to the mass of that packet of fluid particles times its acceleration. We would get the same approach if we did this with a control volume and just shrunk it down to a small point in space, but we're going to skip over that for now. All right, the next thing I need to get to, so we're reviewing what forces act on this imaginary chunk of fluid that we're talking about. So back in like chapter 2 and again in chapter 3, I introduced two kind of broad categories of forces. All right, those the ones that motivate the motion or the pressure in a fluid. And who can recall, what we call those forces? Just looking for like two, like type A, type B. Yeah, here we go. Body forces and surface forces. Good. Body forces surface forces. And what would we throw into each of these categories respectively? Body forces, there's really only one that we're worried about, and that is going to be gravity or weight, right? Gravity causes the force, but the force itself is weight. So weight and the weight act through the center of mass, right? So that's the definition of body forces, or forces that act uniformly on the fluid everywhere. And so in the case of gravity, or gravitational force, that means it acts through the center of mass. Surface forces, there are really two things that we look for in surface forces. One of them we dealt with in chapter 2, right? Rho GH, pressure, yeah? And the other one is the one that we have been ignoring up until this point in the class. We haven't been using it in any of our equations of motion. We've been saying, forget about it. Huh? Friction or shear stresses, right? Or shear forces. Shear. All right. So we have these three kind of main constituents of forces that are going to be acting on a body or a chunk of fluid. So let's imagine that we've got face of some fluid element, right? This is just the surface of a fluid element, and we're going to say this has some area delta A, right? This thing is going to have we're going to define a local coordinate system on this. That is, we'll say that this is the normal. We'll say this is unit vector 1. And this is unit vector 2. That is, we're not using XYZ at the moment. We're just defining an arbitrary coordinate system we put on this thing where we've got a normal and then 2 that are in the plane of this little surface element, but are orthogonal to each other in that plane. So we can define forces in each of these directions. Right? We'll call this F1. F2 and Fn. And together, let's see if we draw this out. So the resultant force, this thing we'll just call F, right? So what we're getting at here is that there's a force acting on this which we're decomposing into 3 components. One that's normal to the surface and 2 that are in the plane of that surface. And the reason we're doing this is because normal forces tend to act because of pressure, right? Forces along a surface tend to act as a result of shear. So in a more general sense, if we wanted to say, all right, I should make these all really small forces because we're dealing with a small element. Remember, we define, we say the normal stress on this thing, that is sigma nn is equal to delta Fn for delta A. We could say that the shear stress, tau n1, is equal to delta F1 over delta A, and the other shear stress, tau n2, is equal to delta F2 delta A. All right, this is the same thing we dealt with before when talking about the stress tensor. You've got forces, you've got a small little area, force divided by the area, you get units of stress. In this case, normal stress acting as a pressure, and 2 components of shear stress. So, taking this, we haven't yet put this into an x, y, z coordinate system because I wanted to illustrate that any force acting on the surface of a body can be decomposed into these 3 components. That is a normal force, or a normal, and which shows up as a normal stress, and the 2 components of shear stress. However, this body's orientation, the surface orientation, is pretty arbitrary. So let's go ahead and imagine now that this face is attached, instead of floating around in space, that it's attached to a cube, and this makes up the side of a cubic fluid element. Now, just like we've done all this before. I say x, y, z. On each face, then, this means is we have 3 stress components. Who remembers what this one here is called? Sigma xx. This one. There we go. Well, sigma tau, right? Tau xy. Tau xy. Tau x and z. And we could go ahead and just go around and fill all of these stress components in. We have tau zx, tau zy, tau, sigma zz, and so on and so forth. So that's great. All right, we can write out what these stresses are. We can put the signs on them. But what we're really interested in figuring out is what the resultant force acting on the body actually is in each of our component directions. Right? So the way we're going to do this is our favorite series, Taylor series expansion. Right? So I know everyone hates this stuff, but it makes the world go round, I swear. So I keep drawing different views of this thing, but let's imagine we're looking at one of these faces here. So we've got xx, tau xy, let me make this instead sigma yy. Alright. The idea is if we know the stresses at one location on the body, then by Taylor series expansion, we can write out the stresses on other parts of the body over here. We would have sigma xx plus partial sigma xx partial x delta x, right? If this here is delta x long. Over here we would have tau xy plus partial tau xy partial x delta x. And we could go through this whole process, same thing over here. We would have sigma yy plus partial sigma y, partial y, times delta y. And what we would get is then, if we wanted to write out the forces that resulted on the body as a function of these distributed stresses, we would get in, I need to make room for myself. That in the x direction, we would get partial sigma xx, partial x, plus partial tau yx, partial y, plus partial tau zx, partial z, all times delta x, delta y, delta z, I. In the y direction, we would get partial sigma y, partial y plus partial x, y, partial x plus partial tau zy, partial z, also delta x, delta y, delta z. It's in the j direction, and finally z direction. Alright, so these are our surface forces on our little element of fluid, right? And our body force is simply going to be, so this is F sub S, our surface forces. And our body forces we simply write as, it's just going to be rho delta m g, right? Which we could say is rho delta x, delta y, delta z times g. So this is just the weight of the element acting through its fluid center. And because I don't feel like writing this out 6 times, I'm going to put it back up on the projector screen. So, we're going to do that. Okay. So we have our x, y, z components of surface forces, like we just said, and our body force is going to be acting through the center of the element in whatever direction gravity is pointing. And so we get the total forces on the body then are just equal to the sum of the surface and body forces. I'm going to keep my eraser down somewhere. So let's not lose sight of what we're actually working on here. So we have, this comes from surface forces plus body forces. This we just have equal to rho times the differential volume of the element. And then how do you think we write acceleration of a little packet of fluid particles? Dealt with this in Motion Chapter 4, right? We're talking about now a system, essentially, right? It's a point in space. it's a fluid element. So this is the Lagrangian acceleration of a fluid element, and all we have are field representations. We're going to write this as the material derivative, right? We're going to say that this is equal to the Lagrangian rate of change of the velocity. And so plugging in all those elements, we get this mess. So, conservation of linear momentum can be broken down into these three components. Total forces in x is due to acceleration in x times delta m, y, z, and if we just expand out all these terms, what we have are the force terms, rho times the gravity in the x direction, y direction, z direction. These are the expressions we came up with for the surface forces over halfway behind the projector here. And then over here we have rho. We went ahead and divided out the delta v, the delta x, delta y, delta z. This shows up on both sides of the equation. So it's already been factored out here. And then this is just the material derivative of the velocity field, this component here. And so there's nothing here you haven't seen. This is all just plugging in things that we've done up to this point. But this is actually a really nasty set of equations to work with all the time. And so I think that actually runs us out of time for this lecture. But in the next one, we're going to be talking about simplifications that you can make to these general equations, right, that allow us to actually do something useful with them.
I wrote down the first one. That's the only one.
Our best friend getting this one
Alright.
I can't send it.
No one else to do.
I should have typed out on the card and I sent it anyway.
That's where we want to expect it. Well, take your flip on both.
Okay, see, I just want to remind you, I'll be here Monday, but I won't be here Wednesday or Friday.
Right, same meeting, right?
Yep.
Okay, yeah.
I'll
Make
just
sure
let you know.
that all of the lecture recordings should be posted if
Okay,
you want to.
will you record it with like the camera, or?
Yeah, just on Canvas, how there's the lecture recordings tab.
Okay.
All the lectures are posted up there, so you can just catch up there. Yep.
I have a quick question for you.
Yes.
I'm from Campus Computing Science. We have like printers throughout the campus. I was wondering, for this building, where do you do your printing?
I don't actually work in this building except to teach this class, so I have no idea where the printers are.
We have one printer here that's not getting any use. That's why we have to find a better place for it. So